Hello everybody, today we will be talking about the heat exchanger design project. For this project we were tasked with designing the heat exchanger for water cools engine oil. We are given the oil temperature going in and out as well as the temperature of the water coming in. This will be a counterflow system using the shell and tube heat exchanger design. So first we calculate the heat transfer rate using TH in, TH out, M dot oil, and CP oil. TH in, which is the oil coming in, will be at 100 degrees C. Coming out, it will be 80 degrees C. M dot for the oil is 8 kilograms per second, and CP is 2132. All those plugged into the Q dot equation for the heat transfer rate gives us a heat transfer rate of 341,120 joules per second. From this we can solve for all the temperatures by using the correlations that the Q dots are equal to each other. So with this, Tc out is equal to Q dot divided by M dot Cp plus Tc in. But in this case, the M dot is 2 kilograms per second for water, and the Cp is 4182, once again a property of water. This results in a temperature of 60.78 degrees Celsius. Next up, we can solve for the surface area with the LMTD method. So for the surface area, we have A is equal to Q dot divided by U times delta T Lm. Delta T Lm is described as T1 minus T2 divided by the natural log of T1 divided by T2. T1 for a counterflow system is TH in, which is the temperature of the oil going in, minus Tc out, the water temperature going out, and T2 is described as Th out, the oil temperature going out, minus Tc in, the water coming in. Q dot, which is seen on the previous slides, and U is a new one that is a given for this problem. With these numbers, it results in a surface area of 3.54 meters squared. Next up, we can solve for the effectiveness. The effectiveness is given from the NTU method for a counterflow system with a C value of less than 1. So with that, we use our C minimum, which is M dot times Cp, which results in a value of 8,364, and the C maximum of M dot Cp, but for the oil this time instead of the water, of 17,056. The equation seen at the top there is the effectiveness equation, and the overall effectiveness for this system is about 51%. Next up, we can solve for the design, or the size of the system, So in this system, the volumetric flow rate is 0.002 cubic meters per second. This is given from dividing M dot by rho. This is of the water. For the flow velocity, this is a number that we can choose, and I am choosing 2 meters per second as a given velocity. This results in dividing these two numbers out results in a flow area of 0.01 meters squared. This is where we can also pick the diameter of the tubes. So for this, the inner diameter of the tubes will be 10 millimeters, and the outer diameter will be 15 millimeters. So to determine the number of tubes, we use the flow area divided by the area of the inner tube. Dividing this out, we get a number that is right around, as a bit less than 13, so overall we would need 13 tubes in this system. From this, we can determine the length. The length is determined by the area divided by pi times the diameter, the outer diameter, times the number of tubes, which results in 5.78 meters, which means that we will have a system with 13 individual tubes. Each of them are 5.78 meters. So in this, I have shown you the size of the system, the effectiveness of the system, all the temperatures within the system, as well as the heat transfer rate within the system. Thank you for listening.